All right, let's go ahead and get started again. I hope you guys got some coffee, got caffeined up, ready to finish out strong. All right. You guys excited to take on random forests? Yeah, get lost in the random forest. All right. So far we've gone over confusion matrix, decision trees done, IPython notebook done, and we've done ensembling, and now we're doing random forests. So I think that you'll be pleased with how little you need to know to understand the random forest algorithm based on what you already hopefully understand from the decision trees. But to give some context for the motivation behind learning random forests is, or just some context, it was invented in 2001. So very, very recently, 14 years ago. The paper is something I include a link to here. If you're interested in learning more about the theory of the random forest, I'd highly recommend checking out. I thought it was really accessible. Like, I don't have a graduate degree in math, and I thought it was really accessible. I thought it was very readable, and I was able to follow along with it for the most part. In the paper, and I'm going to sort of include some quotes from the paper that sort of define what the random forest does and doesn't do, and what the benefits of it are. And in the paper it says there are 5 benefits to random forests. The first one being accuracy, the second one being relatively robust to outliers and noise, the third one being speed, and it compares to two other tree-based ensembling techniques, one bagging and the other boosting. If you're interested in learning about bagging and boosting, I have a portion on later on in the notebook. Bagging I don't go over, excuse me. But if you're interested in learning these and talking about them, I'd love to chat with you during office hours. The fourth thing, it gives useful internal estimates of error, strength, correlation, and variable importance. So it is a model that is powerful, it's accurate, it's fast, and it's also interpretable to an extent. And this variable importance, it's the same variable importance that we just covered for the decision tree, except it's averaged over lots and lots of decision trees. You still got features associated with variable importance factors. That's really nice. And then it's simple to understand. It's easily parallelized. You'll see why that is the case in just a moment. So what is a random forest? Here is the definition. It's just 2 lines here. Each new training set is drawn with replacement from the original training set. Then a tree is grown on the new training set using random feature selection. The trees grown are not pruned. And that's it. Now you understand random forests. Have a good weekend, guys. No, just kidding. So it is a very simple process. You draw a sample of data. First step is you draw a sample of data, a training set of data. This is the set of data you're going to train your model on. You got 100 points, you draw 70 points. Then you grow a tree, but instead of just growing a tree the regular old way we are growing a decision tree, looking for the best possible split of each node, each time you choose from a random subset of features. I'm sorry, yeah, random feature selection. A random subset of features. So let's say you have 10 features in your data sets. You got passenger class, siblings, spouse, parents, children, age, gender, all these different things. Instead of looking at all the variables like a decision tree would, it looks at a subset of those features. Let's say it only looks at 3 features each time. And it's random. So the first split, it considers gender, class, sibling. Second split, it looks at spouse, age, passenger class. Third split looks at gender, sibling, parent. And it's different. It's different each other. It's random. And so that's where the randomness comes in. So just to visualize what's going on here, this is the way that I think of it. This is the way that I remember it in my mind. Can you all see if I write over here? You guys see that? Okay. Very good. Okay. you've got your features here, x1, x2, x3, x4, and you've got your observations here. And what you do is you take a random subsample of the observations, and that random subsample is going to be the training for the entire tree. Okay? That single tree. And then within that training example, each split, you take a subset of the variables. So you're essentially, let's say, I'm going to take the second observation, and I'm going to take the 0th observation, and that's going to be my data set. I'm going to take some observations down here. That's my data set for my first decision tree. I'm going to create a lot of these decision trees. That's my first decision tree. And then for that first decision tree, the first split, I'm going to look at x1 and x2. The second split, I'm going to look at x2 and x3. The third split, I'm going to look at x3 and x1. The tree after that, I'm going to look at x2 and x4. And you keep going iteratively in that fashion. And you don't prune the trees at all. There's no pruning. There's no stopping. Pruning technically means you grow a tree out to its full extent, and then you clip off branches. That's not how it's implemented in scikit-learn. In scikit-learn, which is what's common practice, you just specify a stop. There's no stop. You keep splitting until you get down to you can't split anymore. That's how random forest works. Before getting into why random forest does what it does, is there any questions about what random forest actually is? How it's actually working?
Does it do every single combination, or can you specify only do, is there a way to say do every combination or only do 20 combinations?
Of variables?
Mm-hmm.
Yes, there is. Yeah, that's one of the parameters. So there's 2 tuning parameters for a random forest. I mean, there's more, but two commonly referenced tuning parameters. The first one is the number of variables. I think it's called max features, if I remember correctly. Max features in Python. The second one is the number of trees. Those are the 2 most important. I mean, Sanam, would you say something different? I would say the 2 most important tuning parameters would be the number of features and the number of trees. The number of features to try out each split.
Yeah, no,
Candidate features and the number of trees to grow.
You mean max features? You mean by number of features?
Yeah, max features.
Yes. Yeah. Okay. I also toggle the genie percent repeat.
Okay.
Because sometimes actually,
Sure.
It's a very easy thing to do.
Yeah.
2 options.
Yeah. Cool. So does that answer your question? Okay. So if you wanted to do max features everything, guess what you'd have? What?
Regular decision.
What? You're still training a lot of decision trees.
Oh.
Yeah, it would just be decision trees. Regular decision trees. A lot of decision trees. Do you know what it's called when you have a lot of decision trees? This is not a joke. It sounds like a joke. The setup is like, what is it called when you have a lot of decision trees?
Random pools.
It's actually bagging. Bagged trees is when you consider all the variables. Bagging, yeah. Yes.
Overfitting more of a concern for since you're not present trees than like normal ensemble model?
Oh my goodness, Alex, what a brilliant question. That is, I was just going to go there. Yes, that's awesome. Okay. So, overfitting is not a problem on random forests as you grow up. Like this is very counterintuitive. Everything we've taught you so far, you don't go too, when the bias period straight off, you've got to be careful. You've got to find that sweet spot of not going too far, overfitting your model on whatever the tuning parameter is. Max true depth, for example, or K, in this particular case, as you increase the trees, it does not overfit your model. It does not overfit your model. adding more trees, not overfitting the model is very counterintuitive. I totally get that. I'm with you. Like, I struggled with the same thing. There's actually a really interesting paper on this that I'm not going to get into right now because we don't have time. But if you guys are interested in reading this paper about why adding more trees doesn't overfit the model, why it doesn't make it more and more and more complex. Basically, what he's saying is like, if you get too complex, then you're overfitting. And what I'm telling you is that adding more trees is not making it more complex. That's really counterintuitive. I totally get that. There's a really interesting paper that talks about that. But I'm not going to get into through here. Yeah. I wish I had a really like explanation for that paper. Yeah.
When you say max features, so you have 4 total features in this case, right?
Mm-hmm.
So you're doing combinations of 2, like 2 features at a time when you run each decision tree. So you said max features would be, but if you did, the max features is just referring to the total features.
The total candidate features for each split.
So if you did 4 in that case, then that would just be like 1 regular decision tree.
Yeah.
And if you specify the combinations, does it do? Maybe this is like another like option you can have, but like if you say like, say you want to do 2 and 3, like if you say 3, does it do just combinations of 3, or does it do like 3 and less, like combinations of 3, combinations of 2?
Well, it's always going to make one split because these are still carb trees. These are carb trees where you only have a single binary split, but it's looking at the same number of variables at a time.
Right. No, that's my question. Yeah. So 3 features at a time, like 3 out of that.
Whatever your input is, the default I think is like the square root of like the number of total features, or like the number of features divided by 3 or something like that. Generally, the rule of thumb, for those of you who like rules of thumb, the default value is like 1/3 of your total features. That should be what your value is, your value, your starter value, or just out of the box.
So then, when you come up with like a probability or like for each one of those features for x1, like, and you have x1 maybe like 3 different times, or however many times it appears in the split. Is that then an average, or how is like 1?
There's different options. I believe you can do both. I believe you can do. Actually, I'm not sure if you can do both. I know the one that the general what usually happens is it's just the average every time it appears in any one of the trees. So just as for the Gini index or the entropy index was for a single tree, this is just averaging over many trees every time it appears in the tree. If you got 100 trees and gender found its way into every single one of those trees, you're averaging 100 values.
But it would have to be like that certain split. Like if gender were the first one, that makes sense to average it. But what if it's gender and then class, right? And that's one feature.
Those would be 2 separate features.
Right, but you get one value if someone was male and it was class 3 versus if you'd have another someone who was female and class 3.
Right.
So how do you average it? Like how do you account for the fact that that's 2 different?
I'm guessing I don't know the answer for like 100% certain, but I'm guessing it's just weighted based off the number of points.
Okay.
Yeah. The number of points in that node for the split occurred. I think that would be likely. That's the way it works for decision trees. So. Okay. I do have sort of an intuitive explanation for your question about, your question, sorry, Alex, about why it doesn't, the complexity. Basically, the way that I'm sort of arguing, or the results bear out, I would think of it as like, going back to the survey example. It's like the more samples you draw, the more representative, the more closer you arrive at the truth. Like if you're trying to find the the average height for high schoolers in America, the closer, and there's a truth, there's an absolute truth value for that, but you don't have that truth. You're trying to estimate it. And as you draw more and more samples, you get closer and closer to that truth. But at a certain point in time, you stop getting closer and closer to it. You approach diminishing marginal returns as you draw in more and more samples. And so that's what I'm saying. Having more and more trees, the averaging is like. You get closer and closer to the truth, but you start seeing this tapering off. But it never becomes a bad thing. Like having more votes never becomes a bad thing. Just like having more samples never necessarily becomes a bad thing. It never decreases the accuracy, as long as there isn't a bias. And that's what the decision trees provide. Low bias, high variance. Decision trees, low bias, high variance. Their local fit is very good. The low bias. And averaging them all together, they have a low bias. Because some are wrong, and the wrong ones and the wrong positives and the false positives and the false negatives cancel each other out essentially over the average. And then you also have a lot of true positives and true negatives.
So, that makes sense to me, but it's not that you're getting closer to the average. Like your example of mean height.
Mm-hmm.
You're not getting closer to the mean height of the population. You're getting closer to the mean height of your sample. So does that make it less generalizable? You use this model.
No, because when you're evaluating the trees, and that's what we'll do in a moment, we're not evaluating it on the sample we trained on. We're evaluating on a sample we left out. So we are trying to estimate its ability to generalize. Yeah, and that's what cross-validation is doing. It's leaving out a subset, and then it's evaluating on that subset. Yeah, does that make sense?
Yeah.
Okay. All right, we're getting into a bit of theory crafting here, so I want to keep moving on. Great questions, those. I love those questions. I love talking about these. Yeah, I included. I won't go over that. This is some data that he included in his paper, and it showed a couple different data sets and error rates for the decision trees, the add a boost algorithm, and the random forest. I created a data visualization of it, which I put up there, and the random forest, which is the blue, has compared to the orange has a pretty consistently lower error rate across all data sets, which is very similar to what we saw earlier with ensembling results. Okay, so for the last hour of class, we're going to do an interactive exercise. Finally, hands-on, no more theory, just code, and a little bit of theory maybe. So if you have and this one I actually did not give you the answers. So for those of you who were looking ahead last time, you can't do that this time. You got to actually do it. But this shouldn't be that difficult if you were following along with the CART model. What I'm asking you to do in this exercise is to create a random forest. Just go to the website, look up the documentation on scikit-learn for the random forest classifier, and basically just create a random forest, create some predictions, and evaluate the accuracy of those predictions in the same way that we did with the decision tree that you have code for. So follow that same process of, which you see replicated here in the IPython notebook, which is instantiating the classifier, fitting the classifier, predicting the probabilities on the test data set, and then computing the ROC AUC score using the test data set. So basically replicate this process. Take a moment and look at the documentation, random forest classifier, and then see if you can't create a random forest classifier without any of our assessments, just sort of on your own. And then we'll come back and we'll talk about it together. All right, let's finish out strong. All right, so I'll just briefly go over the code. I'll upload this to the GitHub repo as well. But as many of you I'm seeing have figured out, the syntax for implementing the random forest classifier is fairly straightforward. Here you see my random forest classifier The only argument I'm passing to it is the random state argument. And you see, if you run the code, all the different options you could pass in there. I'm just leaving default values for everything just to make it super simple. And I'm calculating just out of the box, what is the ROC AUC score? Here I get out of sample AUC of 83%, whereas before for the decision tree, again, not specifying any parameters, I was thinking 73% versus 83%. So you see a pretty sizable increase. However, that being said, decision tree, I didn't give it any tender loving care, so I'm not surprised that it didn't do that well. But that's one of the main points about random forest. You don't necessarily have to do a lot to it to get significantly better results. It's for that reason that a lot of people, go to the random forest for these kinds of, Kaggle competitions. Question number 3 was calculate the feature scores for the random forest. This is just the feature importances, aka the variable importance scores. Here, I just created a data frame that compares the cart to the random forest. You see very similar, very comparable values. They're different, of course, because random forest is based on a lot of different trees, and there's some randomization thrown in there. But by and large, they're very similar to each other. The next part is asking to tune across multiple values of the trees. And so I'm going to tune across the number of estimators. And I'll go ahead and run that, and then I'll plot the results of my tuning grid. I am tuning across 1 to 30 in 2 increments of 2, and then also 30 to 101 increments of 10. So I have a more dense tuning grid for the lower values and a more spread out tuning grid for the higher values. I wanted to show you how to do that. So let's go ahead and visualize what that looks like. And this is the result that I get. So I'm going from 0 to 100, and you sort of see, maybe 10 estimators, 10 or 11 or 12 estimators might be a good choice for the number of estimators in this particular example, and you see this tapering off effect, which is sort of what we were talking about earlier. The reaching a point of diminishing return. So with this specification, you're not really going to get better than 84%. Is what it's looking like. So the way to improve this further, my takeaway from looking at this is this is probably the max I'm going to get for random forest given the specification. I'm going to go back to the features and try to introduce some more interesting features out of this. Because the random forest, it is automated. It's automated in the sense that given the features you're providing, it's automatically choosing which ones are the best, and it's trying to account for these correlation between the features. But it's not automated in the sense that it's not creating any new features. It's just taking the features you're giving it to it. So if you want to improve it, you can simply by adding more features. Adding, was there a religion, was there a reverend in the person's title, like Sanan mentioned, or was there an MRS versus Mr. and trying to determine whether they're married or not, trying to determine how many family members they have on board, or splitting apart with sibling spouse variables. Those are all things that random forest is not doing. You're going to have to do that. You're going to have to grapple with the data and wrangle that information out of it. Yes?
This may sound like a crazy question. How do you define
I love crazy questions.
How do you define a feature? So I'm thinking about using random forest for a time series. Would the random forest algorithm know to look for lags, look for different dimensions of one feature while it comes up with the best model? So for example, like, yesterday's weather on tomorrow's sale of ice cream. Or do you have to feed it a new version of the feature that represents the lag?
You have to feed it a new.
Yep.
Okay, yeah. It's the same as any other model in the sense that it's
Yeah.
engineer features for you.
Yeah.
Unfortunately.
Yep.
Okay.
That would be considered a different feature.
Yeah.
Okay.
I mean, you could say, you know, a new feature would be how many days from the amount of time since daybreak. You know, that would be like a quantitative continuous variable that you can include, and you've got the hours already there. But maybe that would be a better feature. Or I don't know, the distance of time since a holiday or things like that. You would have to explicitly provide these things if you wanted them to be included as features in your model.
And so for like a continuous response variable, would random forest take into consideration like multi-collinearity? I can't say that word.
Yes, they would.
They would?
They would, yes.
Okay.
That's one of the benefits of using decision trees and random forests over against logistic, linear regression methods. It sort of it deals with these interaction terms. That being said, we're running out of time, and I need to wrap up some things, administrative things. You have to do a quick comment, Sanan?
Well, a comment in the form of a question. If random forest takes care of all these things, why go back? Once you go random forest, why go back?
What do you mean?
Because it sounds like, it's taking care of multiple linearity, it's taking care of features that aren't so important and robust against them. So what benefits, or what are the cons, I guess?
What are the cons of random forest?
There are pros. What are the cons of random forest and decision trees? There are some.
Okay, so here is the here's the 30-second answer, because we only have 30 seconds, so we're gonna wrap things up. The 30-second answer, Josiah's interpretation of the 30-second answer would be the computational speed. Doing a random forest regressor versus a linear regression, random forest is going to take a lot longer because you're doing all these splits, you're doing all these trees. And when you have a huge feature set, that can take a long time. Like if you have a text feature set, like a lot of you have, it can take a long time. Versus naive Bayes, which is a much simpler computation. It's just looking at the probabilities, by class, the probabilities for each feature. And then it's using that to make predictions. That being said, the other thing is that, looking at your data itself, does the data look like it has, like in the case of a random forest, this is the last thing that I'll say, then we've got to move on. But let's just say you've got a simple case, and we'll just call it a decision tree, but by analogy, it would be extended to other cases. So you've got X and you've got Y, and you've got something like this. What is the random forest going to do? It's going to try to find a split. So this is a continuous. This is a random forest regressor, not sorry anymore. It's going to try to find a split. So where's it going to split? Well, probably it'll split right here. What's the prediction value going to be? Well, here it's going to be this, and then here it's, or not that, it's going to be halfway. So it's going to split the decision space like that, and then it's going to, the mean value is going to be a prediction here, and the mean value is going to be a prediction here. It's there's this jump here, which is not really how the data behaves. But if you have a linear regression, then you're going to have this. So I would say if you look at the decision space, like maybe in 3 dimensions, which I can't draw, but I'm not going to try to draw the decision space in that image. But if you look at the decision space, it's going to have these jagged edges, which are going to be smoothed out to an extent with a random forest, but it's still not going to be as smooth as like a linear regression. So the speed and just the shape of the relationship. That makes sense. But and there's other things, the parametric assumptions. Random forests don't take into account any parametric assumptions. They're not assuming like the data has some kind of underlying distribution. But as a result, you don't have the same amount of statistical inferential clout behind it as you might with a linear regression. So if you're an economist who cares primarily about inferential clout, inferential ability, then you're going to prefer like economists. I don't think probably would use random forest regressors. Yeah, they probably would use a lot of these techniques. Whereas a data scientist or someone who's trying to just make predictions, would use random forest, which is what the Cato combination is primarily concerned with. So it comes back again to this statistics, machine learning, interpretability, accuracy continuum. There's George Bach said every statisticians like ours have a bad habit of falling in love with their models. And I think that's so true. You shouldn't just rely on one technique. There's different techniques that are better in different situations and different data sets. That's what my conclusion for that would be. So we can talk more about this. We could talk about this for a long time, but I wanted to go quickly to your assignment for the next week. First of all, just an announcement. My office hours this week are usually on Tuesday. This week they're going to be on Wednesday. On Wednesday from 5 to 7. I'll send out a message on Slack reminding you of that, but they're not going to be on Tuesday. They're going to be on Wednesday, 5 to 7 here. Sanat, are you having your office hours here after class? Okay. Okay, so that announcement out of the way, your assignment for this week is twofold. One part is optional, one part is mandatory. The part that is mandatory is to give feedback on 2 student projects. Which 2 student projects, Josiah? We're assigning those student projects, and you'll get an email with or a Slack message with who you're going to be reviewing. What are the expectations, Josiah, for the feedback that I should give? Should I just look at it and just tell you what I think? We actually wrote up some guidelines for this, and basically the expectation for you in providing feedback is that you read everything they wrote. You read all of the text they wrote. You look at the code they wrote. You try to understand that. You look at the data if they provide data. I understand some of you can't provide data because proprietary nature of what you're doing, but if you're doing Kaggle competition, there's no reason why you shouldn't provide data. Try to understand the person's data. Try to understand their code. Try to provide them thoughtful comment. Think about what kind of feedback would I appreciate. The kind of feedback I would appreciate would be, what do I understand? What is clear? What's not clear? Do I have any suggestions? Do I have any feedback on, oh, hey, this was a really interesting bit of code that you wrote? Any kind of feedback like that, suggestions for how you can take this project to the next level going forward. Feedback on roadblocks would all be very useful. We're expecting that you spend at least an hour per project reviewing and giving feedback. So that's sort of the expectations for that. Okay, any questions on that? So get the beginning of communication by the end of the weekend at the latest about that. So have that in by next week. And then the second one was just an optional assignment, is to take what we've done in class and build upon it. We've talked about a lot of things conceptually. We haven't had time to implement everything, but we've talked about a lot of things, and I think you'll probably have some ideas of your own about how you could take what we've done in class and build upon it. And the way you can test what you're doing and the validity of what you're doing is to create your own Kaggle account and create a submission using the same Titanic data set. This Titanic data set pulled directly off of Kaggle, so exact same everything. Some ideas for things that you could do would be to come up with a more, we mentioned some of these in class, come up with a more sophisticated method for filling in missing values, interpolating there. Tuning across different parameters, trying to tune across 2 parameters at the same time. Try to tune across entropy Gini as well as number of estimators, number of trees. And see if you can create a visualization that shows that and picking the best model from that. Trying to do additional feature engineering, splitting parents and children, which sounds horrible, but you know what I mean. Splitting siblings and spouses, doing regular expressions, interpreting the textual information that describes the person's name. Trying to implement an extremely randomized tree. The difference between an extremely randomized forest and just a regular random forest is that the regular random forest is trying to find the best split for every variable it's considering and its random subset. Extremely random forest just takes a random cutoff value, so like age. It doesn't look at like the difference between 10 and 11 and 12 and 13 and 14. It just takes 15. And how does age 15 cutoff compare to male, female? Compared to passing your class. So see if that improves your results. You can try the AdaBoost. I included materials that describes in a lot of thoroughness what the AdaBoost algorithm is doing. And you could try experimenting with that. I have code at the bottom for that. But if you create a submission for this and you submit your code on the DAT6 student repo, we're happy to give you feedback on that. And the advanced, if you really are up for a challenge, is to create your own ensemble using different modeling techniques. So you create different modeling techniques and then combine them together through a vote or some method of your choosing. Say, I'm going to create one technique using random forest, one using canon, one using logistic regression, understanding that each have their own strengths and weaknesses. I'm not exactly sure what those are, maybe, but see if I can put those together, make a group vote, and how does that compare to the random forest by itself? So there's a lot of different ideas. This is not something I'm giving you to be like overwhelming, but if you want to do this, these are some ideas for how you can take what we've done and build it. Or just apply some of these ideas to your project. So that, I think, is all that I had. Sanad, do you have anything else to add? Okay. Do you guys have any questions about expectations for this next week?
There are 2 classes left.
Okay. The last thing that I'll say, 2 classes left before the presentation. So the last thing I'll say, you guys should have received a survey, and we would really appreciate it if you could just take a minute now, just take 1 minute, just fill it out real quick before you pack up your laptops. And if you haven't received a survey, just let me know. But GA should have sent you a survey. Did you guys receive one?
Just now.
Just now?
Or a few weeks ago. Or like.
Just today. Oh no! Oh, never mind. Never mind then. They must have stopped and not told us about it. Okay. All right. Well, have a great Sunday. And again, my office hours are going to be on Wednesday, and Sanan's office hours are starting right now.
Thank you.
Yeah, no problem.